So good afternoon, everyone again. Welcome to my talk. And this is titled Towards Efficient Virtualized Network Functions for Machine Learning in the Edge. Okay. So by now, I believe all of you are aware of what the cloud is, how the cloud computing operates and works. But the new things that I'm adding to this is in terms of the virtualized network functions and what we call the VNF cloud. So in this context, my agenda, like half the background was explicitly covered, and I thank you again for covering all these details. So I'll directly jump into the agenda of my talk today. So first, I would like to introduce you to the network function virtualization. It's been a phenomena as such, and that's been radically changing the way the clouds are deployed and what we call as NFV cloud. And in this context, I'll begin with a brief introduction, give some background, and then posit the research challenges that we need to address in this space. And accordingly, I will present my work in terms of how we try to address different challenges, and one of them being the performance challenges that we try to address in terms of NFV cloud for scheduling and resource utilization. And then, of course, you know by cloud, you have to provide a fault tolerance and high availability, which is very critical for the operational point of view. And it is also true for the NFV cloud. But however, the way the NFV brings into the cloud, the requirements change. And for these, we need again to rethink on how you want to build the fault tolerance and high availability. And in this space, I'll present about how we do our NFV efficient migration framework and try to build a failure resiliency. And recently, the trend has been towards trying to bring the machine learning and inference and also try to integrate with edge cloud so that you can provide low latency services. So I would also like to end with a note of work and challenges that we try to address here and leave the set of future prospects that we see in this work, and any eager minds or students who would want to really have them trained towards these and work on these challenges. So anyone interested in working on these proposed research challenges can feel free to contact me anytime. Okay. So yeah, let's get in, right? So by now you'd know the cloud is what it is. It's like it's providing you a resource abstraction through the means of virtualization so that you can provide lots and lots of resources almost on an infinite scale and do that on demand basis, right? So that's where the cloud stands. But then this became very prominent in the early 2000s. By late 2000s, there were two different phenomena started almost in parallel, one being the SDN, and that's what we call the software-defined networking, which tried to say, like in terms of networking, how you want to provide the abstraction. Like you saw, you're providing the overall resource abstraction. With SDN, you try to provide the abstraction for the networking in terms of trying to decouple the way the packets operate versus the logic that moves the packets around, right? So in this sense, what we have is with SDN trying to cater for end-to-end connectivity. And this gels very well with cloud because you will have to handle lots of traffic, and how you can really control and manipulate the way the packets get processed. It fits with the context of cloud and SDN. Now we will see most of the Google Cloud has what they call as a SD-WAN is all operated through SDN. And likewise, Amazon and other people are also moving towards having SDN incorporated. And the other piece being NFV. And this came primarily from the telecom operator side, but nonetheless, a very good intersection with how the cloud operates. Wherever you have these networking devices and you have a lot of devices that need to handle the traffic, you need a means to have them supported in large scale. And that's where this NFV, which is basically pushing for a function abstraction, that means you can now decouple the hardware from software and try to run all the hardware implementations as a software implementation. That was the whole point of NFV. And this again integrates well with cloud. And what now it has led to is what I call as a NFV cloud. And this has been a phenomenal task, not just for the telecom operators, but also for the service providers, as well as the enterprise networks and the data center owners. And in this, majorly what it tries to bring is to provide agile network services. So we'll look into like how these integrations have occurred over the years and what are the challenges that have emerged due to these integrations. So, by the way, I just wanted to inquire one more thing. Like, if at all you have any questions or you need anything, I'm fine with having the interaction based on interaction mode, but I don't know how it's being. Because you have to ensure that all the audience have to pose a question and it goes one by one. Either we do it in the end, that's also fine. Or because if something's not clear and if you need any clarity, it's good that you pose the question then and there. And I'm fine with that kind of an approach also.
So maybe chat also can be used, sir, for raising questions.
Okay, sure. So in case that, because I am not able to see the chat screen, in case
I'll do that, sir. As and when the questions come, I'll read it for you.
Great. Thank you so much.
Thank you, sir.
Okay. So yeah, like I was saying, like this integration and overall what we say as an FVE cloud poses us with a lot of challenges and abstractions. So we look into them. And first, let's try to build some deeper understanding on what we mean by this NFV network functions. Okay. So to give a big picture, this network functions were typically like what we have in traditional world was the middle boxes, or what we call as the network appliances. And these were the default, that was de facto, that's being used in most of the clouds, enterprise and ISP networks. And what we say by middle boxes are basically, like you would have heard of the devices like load balancers, NAT devices that operate in different institutional networks. And you can see like these were all purpose built, meaning they were a dedicated hardware and you had to deploy them at your place, whether it be data center, be it the institutional network, so that you can achieve these services, right? And there were also several other kind of dedicated hardwares like IDS, like intrusion detection for security purposes. You want to mitigate the DDoS attacks, which is very common that you would have heard during the earlier sessions, and also the firewall devices. So all of these in the umbrella of security as a service that you want to provide desired to have these dedicated devices. So you can imagine the whole number of devices that you would have to deploy to achieve these services. And likewise, like when you have cloud and you have different services, you can also have services as special functions. Or like when you are having these over-the-air services like Netflix and others provide, you have typically like ad insertions. Like you will see in the Google, they insert the ads based on what your kind of interaction that you're having, right? So these are some additional devices that you typically install and deploy in your data center or cloud to provide distinct kind of services. And these distinct hardwares providing you different facilities are clubbed as middle boxes or network appliances. Now, earlier there was some study conducted to see like how many of these services are being deployed and what is the ratio in terms of the actual servers that run in the cloud or data centers or even the ISPs versus the mix of these devices. And you can see here, just like this was around 2015, 12 to 15 time, right? And you can see here the number of devices that these devices were in terms of different devices all in networks, like the routers or the switches, which are basically meant to forward the packets. And you can see like across the large scale or small scale, the number of these devices in terms of boxes stand, in terms of how many switches that data center uses, they are almost on par, right? That means the effective usage of these devices has been so high, and that leads to a lot of capital expense for each of the data centers or the ISPs, right? So that, in a way, high volume and diversity. Next, One more interesting aspect about these kind of devices is to note is they are often chained. What that says, if you have a firewall device and if you have IDS, typically all the packets that flow need to go in an order for these packets. So if something is getting flagged from the firewall, need those packets to go to IDS. And if they are not flagged, and you can go ahead with something else. That means they provide different network services on an overall basis, and these services require you to chain the operation of these different devices. And also, like if you have different policies, like the institutions, when you log in from within your network, you may bypass some kind of checkings. But when you log in from outside, you would have to go through this firewall and NAT and so on, right? So that means these devices can also have varied policies to support. And based on the policy, you will have usage in a different mode, right? So the overall background is that these functions are prevalent and they are common, not only common, they are in huge numbers that are the way they are deployed. Plus, these deployments require you to make sure that them properly so that you allow for all the policies to be correctly implemented. So with these as the constraints, let's see what happens when you try to softwareize these devices. So that's where function virtualization kicks in. And ideally, like in the traditional world, you had each of these independent hardwares. Now, when you want to virtualize this, what that means is you want to get rid of these issues that you see with these devices. One being they being expensive, being having them to be deployed statically and getting the configurations done, which is adding to inflexibility. Move to software and then say that, can I build these on top of the commercial hardware that exists in cloud in terms of using the commodity software, the commodity hardware that is the traditional compute, storage, and networking devices, and build these virtual routers, virtual firewalls, all of these as softwares that run on these devices. So that way, you don't have to spend anything for these additional devices, but you can directly plumb them as softwares and you can configure them dynamically, right? Now, because they are softwareized, you can configure and you can scale, meaning you don't have to purchase a new hardware and set it up. You can just spawn a new instance of this virtual router and you have a second instance running, right? So this way, this was the whole view of how this network function virtualization started, and it aims towards providing these benefits. And it's been taken very well because this not only reduces the capital expenses, but also the operational expenses, because if the devices fail, you don't have to go check with the person whom you purchase device and get these updated. Rather, you can have the software to be respawned and rerun, or you can have the software to be, if they have any bugs, you fix them with the software vendors, right? So any failures, it becomes easier to handle, and that way you get both capex as well as opex benefits. And it's also flexible because you are easy to modify and update than trying to get a new hardware and change the entire setup, right? So this is where the NFV started, but the deployment, like we see, is not that easy, especially when we want to talk about the cloud scale. And what that means is this network function cloud, when it has to become a reality, it faces several challenges. And one of them being the management and orchestration, the primary, because when you say that you are taking the hardware and trying to pull the software devices, now you have to run these software devices on some existing compute devices. Now, once they are running, that means how you provision them, how you control the setup of those, and how you manage the traffic and steering the traffic towards these devices becomes a concern, right? Next, let's say you have addressed this management and orchestration, then the immediate question comes is performance, and are they good enough to meet that you can replace the hardware devices as is? And that's where, like, whether you are utilizing the resources properly, and now if you are running this as a virtual software, how is it scheduled on the machine, whether the load is balanced if you have multiple devices that are running, multiple of these instances that are running. All these questions come and try to see whether the performance optimization is a necessity, right? And then once you add these, we know, like, the hardware's failure rate is much lower. But while the softwares, they not only fail when the hardwares fail, but they also have their own bugs. And especially with lots of developers trying to develop the code, and bugs are a common phenomenon. That means there is a new dimension to the failure. And what that means is if you want to ensure availability and reliability of your service, you need to make sure that you can address rightly the resiliency for any failures, build that capability. And to build that, you need to see what are the mechanisms that you can do to provide this fault tolerance and achieve high availability, right? And there are also like the security, which more major concern, especially with the cloud, and that also ties the same with the NFV cloud here. But in this context, I would like to stress more on these upper bounds, and these challenges that I have put in the gray are yet there are several of the works that I've tried to address, and it's still an open challenge in many ways to address these precisely. Okay, so this should have given you a picture around how these issues arise when we try to speak about this NFV cloud in terms of resource management and deployment. Okay, so let's begin with the three challenges that we just mentioned and try to see, like, when we come to performance and scale, what do we really mean, right? And when we said the whole goal of this NFV cloud was to replace the traditional middle boxes with the softwareized softwareized components that run on standard servers, right? So if we take a look at performance in terms of how these devices behave, like this CGNAT and firewall, as the devices that were dedicated devices, they can support, you can see in terms of performance, they can support around 320 gigabits per second. And this number is taken from a data sheet. You can also see similar products that try to give you the numbers. And you can see that the firewall can also support around 640 gigabits per second data rate. But when we talk about the standard machines which are operating on Linux or mostly traditionally the Linux servers, or even have Windows or Mac, but even there, the bottleneck now you can see is 10 to 40 gigabits per second. And nowadays it's moving towards 100 gigabits per second. But nonetheless, when you have the operating system, the software stack, network stack, and so on, the achievability of even these 10 to 40 gigabits per second has become a major concern. And you can see like this is almost 10x lower, right? So with standardized machines, you can see the performance has degraded severely. And second dimension that we can see is in terms of scale. When you have dedicated devices, you can plumb the necessary memory, necessary way to handle the data, and you can scale to around 400 to 600 million flows at a time. Like with cloud, you need to handle millions of flows per second. But with standard server machines, you cannot keep track of all the data, and this rate has been like less than 1 million flows that you can scale up to and maintain the state for them. So this provides a two-dimensional ways where you have to think about how you can address this performance and scale. And with early deployment of NFV around 2012, these questions started popping, how to make this a reality. And several researchers tried to work out the different ways and to then see can be addressed. And one of the work I will address in the next set of slides. Second aspect being the management and orchestration. And where this fits in is now we know that these standard servers are around 40 gigabits per second, or you can scale to 1 million. That means if I deploy these 10 times, then I can meet around 400 gigabits per second in this rate, right? So that means you can deploy more instances. You are trying to distribute the load across them and make sure that you can meet up or catch up with what these traditional middle boxes were supporting you. And if you are trying to do that, that means you have to now manage these many different instances and orchestrate how they are being brought up, whether you are trying to meet the traffic demand characteristics with on demand, you want to bring these resources up. So that means now you have two dimensions to address here, that's management and orchestration of these network services. right? And then, like we said, this high availability and fault tolerance is also a third concern. In terms of the traditional hardwares, you can achieve up to 5 nines. What we call in the telecom world is a 5 nines where you have 99.999% availability, which boils down to around less than 5 minutes of downtime in an year. That means the services are ensured to be running over most of the time, except for a few 5 minutes in the entire year span. However, the standard server machines can barely achieve 3 nines, which is having more than an hour's, at least minimum of an hour's downtime in the entire time, provided they can meet up this. And this is much lower, in fact, several hours of downtime in an year. So if you have to catch up and try to provide this availability space, that means that is the requirement from the telecom grade availability, and to meet them, for them to be really deployed, that means you need to have very robust mechanisms that can overcome the failures and allow you to scale. Right? So we will look into each of these scenarios. And first, let's try to start with the performance and scale. Okay. So, like I said, several researchers worked on these aspects and dimensions. And what emerged in the early 2015s were a couple of approaches where they said, we know that these devices, the whole problem lies in how the packets are processed through the networking stack and back into the sending through the Ethernet devices. So what they proposed is, instead of deploying these virtual network functions into different machines, you can try to consolidate them. Make a change so that you can see here that this chain 1 is trying to provide like all the NAT, firewall, and services in tandem. So as the flows arrive, you are trying to process all these functionalities on a single node or a single server and on a single core. So basically, like the research progressed, and they said, why not consolidate all the network functions that you want to provide into one distinct block? And with this, you can see that all the services that run are NAT, firewall, or monitor are all clumped together, and they are made to run in a single core. This way, what you can achieve is a good performance in terms of, because now I can scale these on per core basis. So if my server has 20 or 40 cores, I can deploy these instances 20 or 40 times on a single node and try to achieve this like performance for having them to run on a single core. So that way it will address performance, because major hindrance with performance comes when you have to traverse through the network stack and have the cache issues, cache misses that happen, especially with CC NUMA nodes, and you avoid all of these kind of a deployment. However, now if you want to scale, what this means is you scale this entire green box at a time. So let's say if NAT was operating at a right speed, but firewall had a concern, you cannot say, I will just scale the firewall, right? So it is coupled. That's why in terms of scalability, and typically this is what happens, because you have some functions that take very less time, less compute, while other functions require you to go to IO, do some IO operations. That means there is a drastic difference in the way these network functions operate. So if you were to scale the blob again, that means you are unnecessarily using the resources, right? So that's why, like in terms of performance, maybe they are good, but they hinder the scalability and chain-wide deployment flexibility, because you have to now, the that you want to deploy is this entire blob. And if I want different combination of these, that means you have to pre-program and generate these combinations. That's where this deployment flexibility is hindered. So there were alternatives that started getting proposed in thereafter, and one of them said, why not multiplex, right? So now instead of trying to build them, let's say we build each of these network functions as a small microservices and multiplex them to execute them on a same core. So that way now you get the flexibility that the flows can just go through these network functions as a microservice paradigm, and you steer them without going through the pain of network stack again and get them executed at different network functions on different cores. So what that means is, although there will be some performance, because now you are having to traverse through different cores or maybe handle them all on a same core, you will still get a benefit of chain-wide deployment flexibility, because in this above scenario, if firewall were to be the major bottleneck, you can scale just the firewall instances as many as you want, while the NAT instance can be single, right? So that way, you get the benefit of trying to scale, have the chain-wide deployment as and how you need it. So, and even the scalability is more precise, the control or scalability is good, but the questions come in terms of performance that we want to achieve, right? So this is where our first work that I did starts with, and we try to see like how is it that when you're speaking about these, basically you are multiplexing, and when you are multiplexing, you are at the mercy of the scheduler to schedule these different network functions on your server machine, right? So the question then comes is how to schedule these network functions so that you can utilization as well as improve the performance for these network functions overall. So we started with a question to see like, should we be using the existing Linux schedulers? Because most often when you deploy the Linux servers, you use the whatever the scheduler that comes with the Linux, that's the vanilla Linux schedulers. And these Linux schedulers, we want to see first how they are performing, or are there any issues or concerns they are trying to schedule, because they have been scheduling different processes and different tasks for years and ages, right? So, but what is it that has changed now is only these network functions that we are trying to schedule on top of them, right? So we want to first see where do we stand with these vanilla Linux schedulers. And if you have the background here is Linux schedulers come in two flavors, basically three now, but ideally you have these two flavors. That is, one is a fair scheduler where you want all the users to get a good portion, right amount of portion of the CPU, and nobody gets to see any lag. And then you have real-time schedulers, deadline-based schedulers as a third component, where you want to make sure that you can meet the critical deadlines that you want to meet for and use these as a real-time mode. And likewise, in the Linux, the native Linux that you get nowadays with the Linux kernel, you have like different subclasses within them. Like you want to have a batch mode or a normal mode of operation, which typically is the default one if I change the scheduler, which try to make sure that you run on a virtual runtime. That means the switching activity here is run on a nanosecond granularity. And that means user perceives lag very less often. And these are really good for multi-user and having good IO interactivity based tasks. Well, the batch, it just tries to increase the granularity a bit so that you can run them for a longer time. And in terms of the real time, you have a couple of more classes like round robin or FIFO, where they run on a strict time slice. So you define a time slice and you run those tasks for that time slice unless they yield. And they run on a millisecond granularity, where you want to ensure that, because you want to avoid the overhead of context switches. Although you may have some, you have the way you have the interactivity and IO, but you will get a good churn when you try to deploy these tasks in a round robin or a FIFO manner, right? So our question now is to see, given these class of schedulers and given these different modes of having the schedulers run, how do they fare for NFV workload, right? So what we try to see is the key objectives for us here is the CPU allocation and utilization they are doing, and chain-wide throughput that they are able to achieve, and how the fair allocation of CPUs for the different network functions now that are going to run. So the difference is the network functions are going to be deployed, right? So we try to do these experiments on our test bed and see, like, if we run different network functions, let's call them a dummy network function 1, 2, and 3. And from the network function perspective, they have a requirement that they are going to serve some flows. And the flows will have some rate in which the packets are going to be served. And the figure here shows like NF1 and NF2 are serving about 6 million packets, while NF3, it just needs to serve around 3 million packets per second. And given that now these network functions are scheduled on the same core, that's where the scheduler plays the role. And if we see, like ideally what we expect is that NF1 gets its able to schedule in a way that it can serve all the 6 million. NF2 gets to be scheduled to serve its quota of 6 million packets per second, and NF3 gets to serve just 3 million that it has to serve. Right? This is the ideal requirement that we have when we want to do this. And that's CPU allocation. What it means is if they're all having the same compute requirement, then you typically expect to get 40, 40, and 20, right? But what we observe in reality is different. So we tried with one normal, which was the default scheduler case, and other real time taking the round robin. And we omit the batch and other for this experiment so that the results will more or less were the same. So I'm showing just the normal and round robin case. So you can see here, just by changing the scheduler, the amount of CPU that each instance gets is varying, and this has a direct consequence on the amount of throughput and the amount of data these network functions can deliver. Right? So you can observe that the CPU schedulers are behaving differently, and the reason they are behaving differently is that they are not designed to account for the NF load. So you can observe that in the normal case, all the NFs, regardless of whether it had to serve X number of packets per second, they got the same amount of CPU. While in the round robin, you can see there is a variation in the way that although like all of the priorities were the same, this NF starts yielding because it has within its given quota, it has no more work to do. That means the given amount of work that this has done can be shared, the remaining time shared between these two. And these two contend for the same time, and whoever gets to win serves the majority. Right? And in that space, you can see here that the throughput is also, although of how much CPU they get, there is a variation in terms of how they are behaving, right? So next we try to see, okay, let's see like if we have, like initially we said the network functions have the same amount of compute requirement. Now we are saying let's vary the compute requirement, which typically is the case with the realistic network functions, and try to keep the same traffic. And if that is the case, how well do the schedulers behave? And again, we saw that this variation in the computer requirements of these NFs had no impact for normal, and it allocated the CPU equally. And back tried to give the allocation to those that demanded more work. So you can see here, like although the 10x and 5x, they were more than this compute requirement of NF3, they ended up getting almost the same. While in round robin, you can see here that it was almost in proportion to the requirement of their computation, right? So, and accordingly, what we see that different schedulers are behaving in a different way. And although like this ideal allocation, we can see this blue has exceeded for the round robin case for the NF1, while NF2 and NF3, they have all more or less gotten, like NF3 is ideal, but amongst NF1 and NF2, because they contend for the time remaining, they can get in different proportions, right? So accordingly, this allocation of CPU has a good impact on how the throughput is achieved for these different flows. And you can see a good variation that you see across these schedulers, right? So what that means is these CPU schedulers, regardless of whether you take normal, batch, or round robin, they do not account for the processing cost overheads, like how much of the NFs do they really need for the CPU to execute and process a packet. They don't have any visibility of these metrics. So, and again, we said that these network functions are typically chained. And when they are chained, that means the packets flow from one NF, they get processed, and the next set of packets get processed by the next NF in the chain, and so on, right? And if we deploy this kind of a scenario, now the difference is earlier they were all independently operating. Now they are operating in chain mode, right? So if you have these kind of processes, what we start to see is just whatever the number of inputs that you give, and if you measure the throughput that you achieve at the end of NF3, different schedulers behaved totally different. So if I had opted for a normal scheduler that the Linux provides, my throughput was around 1.5. But if I opted for the round robin scheduler instead, I was able to get a jump of around up to 2.5 million packets per second. That was the jump in the throughput, right? And this is happening because the way these network functions get to content on the CPU and get the CPU, right? So we try to capture those details, and you can see here in the normal case, all got the same CPU. While in batch, it was in order that like NF1 got some portion, NF2 got another, and NF3 got another. And in round robin, there is again a variation, and you can see higher the compute cost, the NF got its more desired time, and that's where it helped us improve the throughput, right? So what this means is we need to see how well these schedulers behave in different dimensions. One, whether they are scheduling these NFs at the right time, and how many context switches are they doing to schedule these different network functions. So you can see here, the overall context switches that happened with normal were around 20 kilo context switches. So 20K context switches versus 1K context switch with round robin. So lesser the context switches is better because you are not adding overheads for context switches. But context switching at the right time is also critical. Otherwise, what happens is if this NF1 in the normal case processed like 7 million packets, NF2 was not scheduled in a timely manner, and that resulted in drop of around half the packets that NF1 has processed before the time NF2 got the time to process these packets. And likewise at the NF3. So what that means is you need to not only know that you want to reduce the schedule context switching, but make sure that you schedule them at the right time. Otherwise, you end up processing the packets and dropping them before going into the chain, right? So these were some of the takeaways that we can get from just the base experiments to see how these schedulers are behaving and what are the characteristics we have to assimilate to make them work better, right? So we can conclude here that the Linux schedulers are overall suboptimal, result in suboptimal performance, and the utilization from the NFP perspective is very poor. So what we need, how we can tackle this further is we need the schedulers that operate on Linux to be load aware and to be aware of the NF characteristic and make sure that they are aware of the chain requirements so that you know that the packets that are processed by NF1 can be processed immediately by packet 2. Its packets are getting ready. You don't want NF1 to keep processing the packets while NF2 never gets scheduled, and likewise in the chain. So all these requirements need to be met for having the schedulers in the Linux so that you can precisely schedule the network functions. These are the characteristic changes that now we need to incorporate over these vanilla Linux schedulers. So that's where my work, NFV Nice, stands. And here we retrospected and checked how do we want to enable these schedulers to have that information. And we said these networks run in a user space while the schedulers are in kernel space, and you have to transmit these metrics. So the way that we say is we need this user space control framework that can schedule and enable any of the schedulers to work precisely as what the NFV chains demand. And in this, what we try to say is we want to be agnostic to the kernel task scheduler. So you may have different variants, and as the Linux kernel upgrades and there can be new additions, you will have different task schedulers also popping up, right? So you don't want to be providing a custom scheduler that will work just for its kind. Rather, you want to build an abstraction and a layer in the user space that can assist any of these task schedulers to work as you need. And that was how we tried to pitch for having the work to be really a generic one. And this way you can not complement the kernel task schedulers. And we borrowed a lot of idea, because here now we are trying to bring the networking space, right? How the packets are processed. And in network, there is plethora of work that try to address like how these hardware schedulers behave and how the packets are processed within the switches or routers. And there is a good plenty of work there. And most often they try to speak in terms of being rate proportional. And we try to see like what is this rate proportional scheduling and how can we incorporate this onto the schedulers that we are speaking on the Linux. And in the software side, like we have seen here, like earlier, we saw whatever the cost in terms of the computation demand is the cost that you want to meet, and rate in terms of the packet rate that you receive at input, right? So you want to have a mix of both of these concepts so that you can have a good scheduling framework. So overall, like we try to take these early understand and these research aspects to see how we can try to build a scheduler which can improve the throughput as well as ensuring the fairness and improving the CPU utilization. So overall, we will cover the major aspects of this work in a nutshell. So our work here, NFV NICE, what it relies on these 4 building blocks. And the first building block is the C groups, which is basically providing a work conserving and proportional scheduling approach. So if you have come across the terms containers and Dockers, you should be aware that the building set for these containers is basically the C groups and namespaces, the other component, where they are trying to provide a scheme that will tell the user space component to ensure that you can limit, sorry, you can limit the utilization of that particular resource, whether be it CPU, be it memory, be it disk. For a process, you can rate limit or limit the usage of those resources and ensure that you can isolate that from the other. So that means if I have a resource and I have multiple people trying to contend, guarantee that this resource is given this much allotment, and that can be managed through C groups. So what that means is you can utilize this to ensure isolation for a given resource access. So we try to use the same C groups scheme and integrate that with the schedulers the way they have to operate. And this, the intuition behind here is if you look at the hardware packet schedulers that are in the networking switches or routers, they are rate proportional, like we said, and they are also QoS aware in terms of if you have different packets with different markings, you can address them then and there. However, the cost is agnostic because every packet are processed in the same way. And there is no chain either because all the packets that are queued are processed in the same way. While the operating system task schedulers, they are aware of. Hello? Was there any question?
No, sir.
Okay. Sorry, I thought that I heard something. In the operating system side, you have these tasks that are cost proportional, like we said, where you have the priority, so you can prioritize the tasks that you want to run, right? So you see that the control mechanisms are different in either ends. But can we combine these two aspects and build the mechanism for the operating system task scheduler? That was our whole notion. And that's where this NFV NICE, how we try to do is, it builds, it not just takes the cost, it also takes the rate and builds it in the user framework, how you can do rate cost proportional. And then it tries to add this intelligence of chain awareness, meaning you at the user space, you know when you deploy, what is your chain. And can we take this information and in a way that you can control the way the scheduler operates. And then you want to have a tunable QoS so that if different network functions require to operate in a different manner, you can control each of the network functions weightage. So we bundled these characteristics and implemented our NFV NICE framework. So in a nutshell, this accounts for both the characteristics of hardware scheduler and software scheduler and tries to achieve a fair allocation of CPU to all the contending NFs so that They are trying to mimic the way these hardware devices would have behaved with schedulers on the software. Okay, so how we try to do it? Let's look into these details. So like we said, the C groups of the kernel primitives that we can use, where you want to set each of the NF's resource requirement. But how you want to set it needs to be computed in a way. So what we do is we build a weight computation logic that tries to see that given the current load for that NF, and given that this single core is shared by different NFs, what is the share of that particular NF's load? So you compute the load for distinct NFs, and you compute what is the total load on a given core M. And for that core, now you want to schedule these. Then you want to find what should be the share of that NF in that epoch, right? So on a high level basis, if I say I have a good timeline and I can partition this timeline in a way that I give the right amount of resources to different NFs. And you can add the priority as a QoS factor that can factor out if you have to deal with different NFs in a different way, right? So to combining all this, what you need to do once you arrive at the different NF of i's share in that particular quantum, then you update this to the CPU share so that you know that your resources are guaranteed to be allocated in this order, in this manner, and the amount of resources that is apportioned is fixed. So this is as simple as the C groups operates. But note, this still doesn't address the chain requirement that we said. You want to know that only after NF1 gets scheduled, you want NF2 to be scheduled. And that is not going to occur with this. It's only going to say how much time the NF1 should run, how much time the NF2 should run in this given epoch, right? But it serves our first primitive in terms of how we try to address. And this, we have to periodically keep tracking because the workload can vary over time. So we need to ensure that we are able to track and update and make sure that in the next quantum, you are able to correctly update. And this, we do it every 10 milliseconds. Okay, so we said we address the first pass, and now we look at how we can address the second scheme, that is chain-aware scheduling. And for this, we use a concept called back pressure. And this back pressure is very common in our day-to-day lives. And we just bring this in networking, also has been studied in wide scope. And we try to take advantage of this back pressure scheme and see how this can be leveraged for our scheduling work. So here, what we are trying to do is, you are trying to, when you know the chain, you want to see for each chain, how can you ensure that you don't process more packets than what the next guy in the chain can process. That is the whole logic. And in networks, this has been studied for years. And the way to give a terminology of how these things operate, like if you have these packets like flows A and B packets flowing, what you have is this NF1 and NF2 are along the upstream side, whichever are A first, and then the packets move towards the downstream components like NF3 and NF4. And this is the direction of where the packets flow. Given such a mode of where the things occur, so you can see a chain here, right? The green chain going from NF1, 2, and 3, and the blue chain where it is taking NF1, 2, and NF4, right? And purposefully, this is being depicted with red to show that this, if this is a problem, what should occur? Like if this is a bottleneck, how do you handle, right? And in networks, this studied, and the way they try to do is like back pressure. But first, let's look at, if you don't have a back pressure, how does all of this work? So what that means is, if you have a set of packets that are processed, like what we say, the flow A, the green packets, and flow B, the blue packets, and as the packets get processed, and we said NF3 being the bottleneck, that means it is trying to slowly process the packets than the upstream NF1 and NF2. In that case, what starts happening is the queue at this NF3 builds up, and eventually what all packets that get processed at the upstream, that is NF1 and NF2, whether it is for the red flow or for the green flow, they have to start dropping because they are now not able to push the packets from this side. While the blue packets, which were going for NF4, they are good to transmit, so that all the green that this NF2 and NF1 is processing are lost, right? So what that means is there is a lot of wasted work here. And this wasted work, like we are saying, like if these NF1, NF2, and NF3 are all scheduled on the same core, they are going to engender not just impacting the throughput or drop here, but when NF3 requires the CPU, it is being taken up by NF2 and NF1 incorrectly, right? So it is called a CPU cycle stealing. Like, we don't want this to happen. And you can eliminate the contention and make sure that these packets can be processed at NF3 at a fast rate. So this results in a lot of wasted work if we don't have a back pressure. That's the basic background. And in networking, the way we try to do the back pressure is, as soon as you know that this NFU is full, you want to notify your upstream component to say that stop, don't send me any packets. And if that is the case, the queue starts building at the upstream components. And this percolates all the way to the upstream. And then you will start seeing that none of the entities here, NF1 or NF2, are processing. So you have totally eliminated the wastage of CPU cycles, right? But you can see that now this NF4, which could have served the blue packets, is also starving, right? So that means you are unnecessarily impacting different flows also. Although you eliminated the wasted work, you are impacting because you are not able to isolate the reason of why this issue occurs. And also, like we said, we have to give a feedback. That means over the network, when you try to give the feedback, there is always a good amount of delay. And if you are on the same CPU and you are trying to have some notification scheme, then every time you have to swap the context switch and then get these updates, right? So either way, there is a feedback delay and this isolation becomes hard. So what we try to do is modify this to suit the NFV requirements. And what we say, because now we know that all these NFs are on the same core, and the flows that are going to operate, I know the chain NF1, 2, and 3. What that means is I can track for the green packets, it is taking the path NF1, NF2, and NF3. And for the blue packets, it is taking NF1, NF2, and NF4. And as soon as the queue builds up here at NF3, you can make sure that you can just directly toggle the state for the green packets because you're processing them in order, right? So if I do that, then all the green packets are stopped from getting processed at either of the upstreams where they are dropped right at the source. While the blue packets, which are not being marked, they can carry forward and get processed at NF1 and NF2, while NF3 can get its own turn to dequeue these packets. So that way, you have achieved the isolation and ensure that you can react instantaneously for those set of flows, right? So that way you have avoided the wasted work and you have achieved isolation and there is no delay in processing. And what this means is if I have this scheme in a scheduling as the bottleneck NF, I can make sure that for that bottleneck NF, I give more priority to schedule and run than the upstream NFs. So this helps us achieve selective per chain back pressure. This is the contribution that we made to ensure that the NFs operate in the way they desire. So overall, our system looks like this. So we have, like on a hardware, like this is a traditional Linux server machine, and you have different set of cores. And as the packets enter through the NIC, we have what we call an NF manager component that is keeping track of how the network functions are behaving, all the network functions that are running. And we partition these network functions like based on like how they are operating into either the running state or waiting state. And then if there are packets for anything, then NF that it can wake up that particular NF and toggle from waiting to running state and ensure that if they have the NFs in the waiting state don't contend for the CPU, while only the NFs in the running state contend for the CPU. And next, for those NFs that are running in this state, you want to monitor and know what should be the right fair share of the CPU for each of these NFs. So once we monitor and make sure that we can build the CFS group shares that we mentioned about earlier, you are able to apportion the CPU correctly so that whatever the C group weights that we update can then be fed to the CPU schedulers to make sure that amongst these running NFs, it is going to allocate the time space in this particular manner. Right? So that's the simple primitives that we build user space to enable the kernel space to use those primitives and ensure that the scheduling is done in the right manner. So this is the overall system framework and how this is evolved. So we tried to say, okay, we implement this and then we want to see how it behaves. Right? So our test bed here is basically the source and the sink nodes that are trying to generate traffic. And we have enabled NFV nice on this Linux server here. And all the three servers are typically the Intel Xeon machines with 28 cores running 2.6 gigahertz. And we try to manipulate only the network functions here and see how the impact on input, what's the input rate and what's the output rate that you achieve. And for that, we use the MoonGen as a traffic generator that can support 10 gigabits per second and almost 14.8 or nearly 15 million packets per second at the 64-byte packets. And iPerf as a TCP flow generator that can generate multiple TCP flows. And remember, we still use the native Linux schedulers, and the native Linux scheduler behavior is what we are interested in, whether we deploy NFV nice or not. Like without NFV nice is the native behavior. And with NFV nice, we want to see how these schedulers behave. We are not building any custom scheduler here. We are reusing the schedulers, but enabling this intelligence that can enable to operate differently. Okay? So first, we try to see like how this chain-wide scheduling of simple NFs, network functions, where we are showing here, like NF1 has a packet per packet processing of 120 cycles per packet, while NF2 takes around 270 cycles per packet, and NF3 taking the largest quantum, that is 550 cycles to process a packet. And we schedule these network functions on the same code so that the scheduler plays the role and we can see what's the behavior. So this is exactly similar to what we showed earlier in terms of how the behavior was. So you can see just the basic schedulers, the normal batch and round robin, they behaved totally in a different manner. Now, we said we built it in components, so we enable just the C group component. And you can see just in the C group component where we just... So when we enable just the C group component, what we said is you are trying to make sure that you are allocating the CPU in right shares. And you can see this allocation in right share has significant impact at the normal and batch case, while the round robin, which doesn't take into consideration of the CPU share because it is just trying to, on the real-time mechanics of whichever is available, you schedule it, it has no impact, right? So it serves half the purpose for normal and batch schedulers. Although the improvements you can see are more in the time case of normal, batch it's a bit less. But overall, like you can see, the improvements are making the normal and batch behave the same way. Right? Next, we said, okay, we talk about chain and how much is the chain that is going to, and we enable only C group and not only the back pressure and not the C group. And now you can see that across normal, batch and round robin, you are able to get improvements in all the three cases. And what that means is the chain awareness is really critical in terms of trying to make the scheduling decisions, coupled with how you want to allocate the resources, right? So that's why now you can see for round robin, there is almost a 2x improvement here in trying to achieve what is the achieved throughput. So then we say NFV nice, which is basically combining these two aspects together and trying to say, like, if we enable both C groups and back pressure, how is it that your schedulers behave? And now you can see that across these normal batch and round robin, when we enable all these pieces, you are able to get better performance in all the three cases in terms of, because you are judiciously trying to utilize these resources, your improvement in throughput is a straightforward one, right? And we try to dig deeper and show why this happened. And you can see with NFs earlier, like if it were just the regular work, we showed earlier, like how much is the wasted work, right? So almost the work that was wasted was more than 50% each of the NF2 and NF1. Now with NFV nice, we are able to bring back this wasted work to less than 1% in either of the cases. So we have reduced significantly the wasted work. And what that means is you can utilize the same CPU cycles to schedule the bottleneck NF correctly, right? So, and you can see how this runtime of the NFs behaves. If you take just the default scheduler, it was apportioning equally. Now with our CPU share mechanism and back pressure, we are making sure that the apportioning of the CPU cycles is more or less in the order of their requirement of weight in terms of how many cycles per packet they need and how many packets they need to process. It is strictly coupled with this number. So that's where this rate and cost are being brought together to say how the CPUs should be allocated to different NFs. So CPU allocation truly becomes proportional to computation cost as well as rate. So the takeaway here is that NFV nice was overall able to improve the throughput for all the kernel schedulers, right? So now we said we did it on one core. Now what happens if you were to deploy the network functions on different cores? And the same holds good with default as well as our scenario, where you can see this deployment scenario here, where we are saying core 1 is dedicated for NF1, while core 2 is dedicated for NF2, and likewise for 3 and 4. So that means scheduler as such is not playing any role here. But the way the traffic is being and transmitted amongst this and the chain property plays a role in terms of how these NFs process. So you can see here, both the chain 1 and chain 2 are getting processed at NF1, while these NF3 and NF2 are distinct for chain 1 and chain 2, while NF4 again is processing both the packets, right? So there is a multiplexing and demultiplexing that's occurring. And now what we see is if you just deploy them in a vanilla system without the NFV nice, the behavior is the NF1 will try to process as many packets that it can and push equal number of chain 1 and chain 2 packets to both these NF2 and NF3. But NF2 being light loaded, it can handle the packets that the green chain processed. But the NF3 being a compute intensive, it can only manage to process very small portion of the packets that NF1 sent. So overall, when these set of packets again converge at NF4, your overall throughput is just the sum of what you can handle at NF2 and NF4, NF2, NF3, right? So overall, your throughput is greatly reduced, and that means even when the scheduler is not really employed, how you are trying to multiplex and allocate the resource for different flows can greatly impact the overall performance, right? Because the red here was lost. And then we say we deploy NFV nice and try to see how this operates. Okay. So once we deploy NFV nice, what this changes is because it is chain aware, regardless of whether the chain runs on the same core or on a different core, the back pressure scheme enables you to know whether you can process the green packets or not. So as soon as you know that the red packets hit a bottleneck here, it signals the NF1 to say don't process red anymore, right? So what that results is the same CPU that it can utilize to process the red, now it can in turn invest for green packets, right? So that's what you can see here. In overall, now NF1 is able to process more of the green packets and just the necessary amount that this NF3 can process the red packets. So overall, now you can see the benefit in terms of the overall throughput that you achieve is almost twofolds. Why? Because you are making sure that you are properly allocating the CPU core 1, to the packets that can be processed downstream and upstream. So even if this were to be here, then it is on the upstream that you signal and make sure that the upstream works correctly. Right? So that way you avoid the inefficiency and ensure that your allocation of CPU is judicious in terms of the requirement of different flows, not just for that particular core, but for the entire chain, regardless of whether the chain spans on a single core or multiple cores. So overall, now if you look at the numbers in terms of CPU utilization, overall numbers would have been like CPU utilizations were earlier around 60 to 70%. Now you bumped it up for all the cores to around 95%, like around 90%. But at the same time, you have increased the overall throughput by almost 2x. So this is a performance improvement that you gain with FV-Nice, whether it is going to be allocation on a single core or on a multiple core, right? So overall, now we can see that we can achieve the chain-wide performance and ensure that the flows get the right amount of bandwidth and enough resources, right? So that's one segment of what I wanted to cover today in terms of how you really need to think and try to see when we have NFs, what is the challenges that we need to address, and still the work is half done and there is still a lot more in this scope we will address in the later part. Next, we try to see if you have these chains and try to see whether how do you want to achieve this high availability and fault tolerance. And that's another scheme of work that I'm going to discuss now. So in this space, let's say you have these as a typical data centers or clouds, like how they are composed of is a set of switches and routers that have these devices. And you are going to have the packets that flow along these and get processed. So what can really happen in any scenario is that you can have these devices that host these functions fail, like the functions themselves can fail, or you have so many of the links that are connected, so these links can as well fail, that connectivity between the two nodes can get broken often, or even these servers that are there can go down, or you want to do some upgrades sometimes, you have to forcefully bring these down and try to set the things. So, right. So you have different kinds of failures that can impact the overall service in terms of where the packets are processed and how they are going to be processed. So the first question now is, if there are different kinds of failures, how can we really quickly detect these kind of failures and ensure that you can overcome those failures? So the standards have been like, if we know that the failures are going to occur, so given that the failures can occur, before the failures occur, can I build a redundancy so that once this fails, the services can be taken over by the redundant system, like the way we show here. If I build a redundant here and if this fails, this can take up the services thereafter. So what that means is, if this is going to fail, you have to migrate whatever the information that you have for all the flows that are being served here and toggle them to be used in this scheme, right? So the whole scenario now becomes like, how can we achieve this proper redundancy and ensure that you can migrate the state so that you can quickly fail over to the next instance without disruption of the services. So in this context, one additional challenge that comes, like this is all being done already for the NF cloud. But when we talk about NFV cloud, what we have to look for is the characteristics of these network functions. And the characteristics of these network functions, one of the thing is non-determinism. Like if you have aware of the distributed system and how the systems behave, given the same input, you may have different outputs at different time, then they exhibit non-determinism. And in reality, most of the network functions that we are speaking about, like load balancers, NATs, and so on, like that maintain the state, they exhibit non-determinism. Like to give a summary, like how this can happen or what is the non-determinism, how this can occur, I'm giving you an example here as a load balancer, simple load balancer that is trying to basically pick one of the backend servers. And we say, let's say there are 3 backend servers that you want to choose from, and your logic goes something like this. You choose number, and based on that random number, you try to choose the server that you want to pick and assign that server. Right? Now, if I execute this logic on one computer, one server versus another server, the output of this RAND would vary at different points, right? Although the same packets arrived, same processing happened, the logic will end up choosing different server at different instance. So that means if you have these kind of characteristics in software, you are going to end up having a lot of non-determinism in processing the packets. And we see like what are the different modes that these non-determinism can get inserted. And one of them being the shared variables, where we have different threads, like we have P threads that try to run different piece of code, they try to synchronize. Now, how you schedule these threads also can add into basically this non-deterministic behavior. And it is not saying that one is right or one is wrong, but it is only that the outputs can vary over time. Right? And any access to hardware, like you are time stamping the packets or you're trying to contend for the IO devices, these all can result in one way or other non-deterministic behavior. And in networks, like we know that when the packets arrive, you want to mark the packets and drop them, like random early drop, where probabilistically mark some packets to be dropped. Which packet you really choose, given the same set of stream of packets that arrive, can still vary, right? So these are all the overall sources of non-determinism, but our goal is to ensure that given such a non-determinism exists, you still want to reliably transmit the state and address this non-determinism in a way that it is not going to impact the correctness of the system. So overall, like when we are trying to build the resiliency framework for NFV cloud, we want to make sure that you ensure correctness. You want to ensure that whatever the scheme that you try to build has low overhead when you are trying to operate in a normal manner. Because if I try to build redundancy and say that now my performance was 10 million packets per second with serving hundreds of flows, and by redundancy I drop it by half, that is no good. You want to make sure that you are still operating at optimal performance or have at least the minimum overhead in trying to achieve this. And in case of failures, you want to be quick in terms of trying to recover and also have a workload that can meet all the workloads and all the deployment models as a generality support. Because we said there are diverse network functions, we cannot target one kind of a network function. So generality is a critical requirement as well. So we'll again try to see how good are the existing solutions, because this research has been done for years. Several of the cloud-based solutions have also been plugged for NFV cloud, and we want to see how these overall works fit. And we see that there are broadly two categories, where one tried to say that you have state that is maintained for the network functions within the network function, just like when you run a different process, all the state that is carried over is tied with that process. Now, in the database and how the servers operate, like the HTTP, REST APIs, HTTP, what you try to do is you have a backend database and you try to store the data, associated data and correspondence of that data in an externalized state. And that's again the same concept that NFs can take and borrow, and that's called externalized NF state. And accordingly, the works try to study, like if you have the local state, you can do the checkpointing base so that periodically you snapshot and update. And one of the early works was this Pico replication that came in SOCC. And then there is a replay-based approach, so that if I can store the packets and then replay rather than checkpointing at every time, I can regenerate the same state whenever there is a loss. And this was a kind of work that FTMB tried to do and around 2015. So the replay builds on top of checkpoint plus so that you can replay the buffered packets and regenerate the state. So it's going a bit step upwards from the checkpoint. And likewise, in the externalized NF, try to use the stateless NFs and CHC. These are the very novel works that came. And we try to see like how these works behave and what is the paradigm that we should be suiting for NF resiliency frameworks. So let's try to get a good understanding on when we say that Pico replication as one of the works, how does it really play and what happens? And if you have the set of packets that are being run, let's say take the same load balancer that is being worked, and if these packets get processed and then it is going to make the updates here, what that means is the state in this network function is updated That's where we are just showing it as a green blob. And as the packet state is updated, you want to snapshot that state so that if this next packet were to arrive and it has to process, the next packet can be processed here correctly. And only after making sure that you snapshot by building this redundant service, you can release the packets. So every time you process a bunch of packets, you have to make sure that any state that gets modified here gets updated here, and then only the packets are released. So we call this a primary, and we call the other, which is a backup, as a secondary. And the way the states build, like you process a batch, you make a checkpoint, and at the time you make the checkpoint, both are in sync, the state. And then you process with the next batch and you go ahead, right? So if we have to build this in a formal word terms, you are trying to have a primary view at here in terms of state. Always the primary grows first, and then primary is synced to the secondary. And after the secondary is synced, the packets are moving out, right? So even the packets that move out correspond to the logic or the state that the primary and secondary are reflected. So the way it operates is first the primary gets updated, then secondary, and then the external view, because the external guy gets to see the packets only after this is synchronized, right? And we try to just be deterministic, non-deterministic in these green and yellow packets, but you can see every time you synchronize, that means you have implicitly dealt with non-determinism, because you are running in a lockstep mode when the states are getting updated. Right? So it's very simple and ensures state guarantee, and it also makes that you are implicitly addressing this non-determinism, but you are making this very high overhead, because every time you are processing a batch, you are checkpointing, and while checkpointing, the processing is stalled. That means you cannot process the packets, right? So you are adding a lot of overhead, and the more you checkpoint, the more stalls there will be, right? So it will have a significant impact on the throughput, not just on the throughput, but the packets were held till this update was done. That means even the latency for processing suffers greatly. And now imagine you have a chain, like you had a load balancer, you have a DPI and other instance, and you are trying to do this for every instance. It just becomes inflexible and not applicable for a chain-wide deployment. Then we saw this FTMB as a work that came and tried to use the replace scheme. Like what it tries to build is it tries to build two additional components, one called an input logger and the other output logger, so that as the packets come, you buffer them as well as you process them here. And as the packets go out, you buffer them as well as let the packets go out. So you can see again in the same scenario, like let's say this load balancer logic were to run, and for all the packets at this instance, you just chose one as the one of your backend server, you would log your output that was you chose one as your backend server. But you let go the packet, so you can still see that secondary was not updated. While the primary had its state, the critical part of the primary state is being logged here, which is very small delta, and you let go the packets, right? So that way you are processing the packets and ensuring that you log only the necessary information while letting the next set of packets to go. Like this can continue for a series, and then over a period after processing some packets, you can do the snapshot like we were doing earlier with the Pico replication. So what that means is your need to replicate time and again is reduced, and your stalls get reduced. And because you are maintaining the state, in case there was a failure, you can basically overcome the issue by taking advantage of this output log, right? So if we say that this instance failed, you have the state here at this point. So, and you also have the packets here, which had really been updating this state. So if I can use this state and use this packets to know that there is a tie-up of this information that I need to look for, then you can make sure that you can process at the secondary exactly the way the primary processed, and that way you get rid of non-determinism. And here you can see that this approach, although ensures that you get rid of non-determinism, you are trying to have a strict correctness approach where you have to have the output loggers info and the input have this correspondence and updates at the load balancer so that it exactly mimics the primary, right? And again, like if you have to have this, that means you need input output logger for each of the network functions in the chain. That makes it highly inflexible for deployment. So the main thing to notice here is as the packets get processed, the primary view is built and the packets are released immediately. So this external view is built, while the secondary is synced up much later point. So the order is primary is updated always, and then external gets updated as the primary releases the packets, but secondary is synced very slowly as and how you need it, and still ensure the correctness. So this is the approach of FTMB, but it faces these challenges. So we try to see, can we take over and see, can we do something better here? And there we pitched our work Reinforce, which is trying to build a resiliency framework for this NFV chains, because we saw that either of the works, it is very hard to have them deployed for chains. And we also saw that there were performance issues. So can we overcome these two aspects with our Reinforce? And we were able to achieve like chain-wide failover in less than 5 milliseconds and local instance failover in less than 100 microseconds, which is much, much better than the state of the art. And our performance overheads were less than 15% for the normal operation, which other works had much higher numbers. And overall, our failure detection scheme also worked in like microseconds time scale. And the state of the art that works for link failures is around few milliseconds. So that means you can see around 10x faster the way we are trying to do it with Reinforce. So let's look in like how we try to achieve this and what are the main things that allowed us to achieve these aspects. So what we built is again like in the NFV nice, the way we took the components, we had the same and we built the NFV manager, and then we built specific modules that enable us to have this resilience. And again, we leverage the input logger as one of the components. And here the packets are logged as and when they are processed by this network function. And as within this network function, we try to maintain the state, that is the network packets as and how you process the packets, what are the modifications that you are trying to do for the packet pool, and per flow state that is being maintained for each of the packets, whether it is processed at each of the NFs or in the NF manager, and additional logger that tries to see how the state is going to be synchronized with different network functions that are running on the same node or different nodes. Okay, and we built this as what we call as a reinforced node, which is basically the NF processing the packets with reinforced components tagged. And here we add the timestamping scheme. Like this is a logical timestamp that you want to ensure that what is the ordering of the packets that you process, and logger that is trying to keep track of what all the packets that have been processed and released for a given flow. That's like how this really works. So the main intuition for us when we looked at the earlier works is by timestamping the packets, it allows you to sufficiently determine what is the chain-wide processing, because as you timestamp the packets, you know at what NF has processed till what packets in that given flow, right? So if we can keep this information, then would it help us determine whether there were deterministic or non-deterministic updates? And if non-deterministic updates, do we really need to know that this information needs to be tagged and updated at the secondary? So the second scheme that we try to say is distinguish the way the deterministic packets behave versus the non-deterministic. So if you know the state updates that happen for deterministic, we know that the replay is going to help you get the updates. But for non-deterministic, along with replay, you need some additional information to make sure that you can synchronize correctly, right? So earlier FTMB works, they just did the same for everyone. Here we try to segregate this and say we need to have a distinction between deterministic and non-deterministic packet processing. And then try to have a checkpoint scheme that can be, rather than trying to do it for every instance, we try to see, keep track of what all has been dirtied. And then if you see that you can access the dirtied information quickly, like using the find first set, you can update them at that instance as and when you need and ensure that the correctness is maintained. And the major challenge, especially with distributed systems, is when you try to update, you have a two-phase commit scheme. And what that means is until the commit happens, you either have a chance. If it fails, you have to roll back. If it works, you continue. But whatever the processing that happens until the commit occurs, till the period that it needs to terminate, you cannot process. But we said, why can't we pipeline this scheme so that you have a pipeline two-phase commit, so that you are keeping track of the timestamp and you know within each pipeline what are the packets that can be processed and what are the commits that need to occur. So these were the key fundamental things that we saw can enable a good resiliency framework. So to elaborate a bit further, what we built is a two-tier redundancy scheme. At first, the redundancy is maintained within the node, where you have, like in each of the nodes, you have a replica. So that if this node fails, this network function fails, you quickly move over to the replica. And if this entire node fails, you have a second hierarchy of replicas maintained for the same NF3 here. So you have two sets of replicas, one on the same node, other on the different sets of nodes. So what we call them as the remote and local standbys. So you are having a different level of redundancy key, and you also have different resiliency levels. What we mean by different resiliency levels is, like we saw, like NAT, it is going to just change the data, and there is no state that is critical in terms of non-determinism. In such case, you don't really need to keep updating and having the updates go to the remote. And in some cases, you know that only the functions, some functions can fail frequently. Then it's sufficient to have just local failover rather than having to do it remote, right? So these are some of the characteristics that we add to say that you can have different resiliency levels to control how this system can be optimized. So to explain like how our approach works compared to like the earlier two that we saw, what we see is if we have the input packets, what we do is as the packets get processed, we are again demarcating the green and the yellow, and we are making sure that the state that this green is updating versus the yellow is updating is tracked. And the packets, you can see here now, the packets got released, all the greens were released, but the first batch of yellow that came was held, right? So any earlier green packets which were deterministic, they are logged here, but they are sent out, while the yellow packets are held. And if you see this state updates, then I have got this batch, I processed one batch, and now we are calling this timestamp as the minimum information that we need to update. So you can see again, like how we try to do, as the packets get processed, we are only updating the timestamp for the green packets. And as the yellow packets arrive and you know that there is a change, then you track and make sure that these yellow packets are held. And any subsequent green packets arrive can be held until you release the yellow packets that are in the chain, because you don't want to reorder them. So as the batch process, you can go on, then we call this yellow as the non-deterministic batch. And in such case, you want to not just update the timestamp, but also checkpoint whatever is the state. So that way, now we will checkpoint the entire state and release the next batch of packets. So that way, now at this point, after this checkpoint, the state here between the primary and secondary are synchronized. Now, earlier we said you would stall if you were to do the checkpoint. Now we said, no, we don't need to stall yet. Why? Because we have marked the timestamping here, and we know that the packets can be processed. While this checkpoint occurs, I have the state that can be updated differently for a next batch of timestamped packets, right? So I can still process the next batch and have the timestamp logged and updated in a pipelined fashion. So that's how you will start to see that you can not just guarantee the correctness in the way these packets are updated, but also give a processing a chance, and rather than stalling, you are able to process the green packets. That is, those who are deterministic, you are able to process. Why? If they fail, you have a chance to replay and rebuild the state. But if this ND, non-deterministic yellow packets, follow another set of non-determinism, then you have a clash, that you have to have two of these non-deterministic packets to be synced correctness. And that's where our system, if it like while one of them is getting checkpointed, the other occurs, then and only then do we have to stall. Otherwise, the operation can continue. Right? So this is how we are able to ensure correctness and ensure that it is low overhead and trying to achieve the chain-wide deployment. Why? Because here we said these packets are all only thing that we need is the input logger, and every node in the system, because of the symmetry that we have built, is a logger by itself, because until it is checkpointing and sending the packets out, this node acts as a logger, right? So you don't need any additional component other than the network function themselves with a store that it is going to use for logging. So let's see this failure scenario. Let's say if this network load balancer were to have failed when it has the state 1, then at that time your logger would have had the deterministic set of packets that you had and a batch of non-determinism that would have caused this state update, right? So in that case, when you replay, you drop the packets that you know that you have already released. How you know that? Because you check this timestamp and see that you have already processed them, so there is no need to process. So there is no additional synchronization required. And next, when you get a new set of packets, you process it and you see that it can work without trying to see what has happened at this load balancer. Why? Because this load balancer never released the packets and the state was never updated. So yeah, this is how you can see that the main thing is this load balancer, it had its own different state than compared to the primary, right? But still the correctness is guaranteed. Why? You are having this to achieve what you really need. These two are always in sync. So that way you have achieved the correctness, although you have allowed the system to divert in the way they behave, but to the end point of view, you have the state always in synchrony to whatever has happened and whatever is shown to happen. And the concept, what we call, is external synchrony that was being pursued long time ago in database community as well as in the storage community from the file systems and others. So that way the overall overheads are reduced, and now because there is no requirement of any components in between, you can deploy this all in a chain. So the major component that we got is a flexibility of deploying them in a chain, right? This is expensive, maybe I'll skip over this. So overall, to summarize, again, we built the same system and tried to see how our network is like using our systems, how the primary and backup behave. And overall, you can see that for different scenarios, when we compare with FTMB and Pico replication, the reinforce that we have worked on achieves the best performance all along. Whether it is a lightly loaded NF or a heavily loaded NF, you are able to get the best performance in all cases. And when you take the chain, and we assume in this just the first NF tries to do, and you hit this bottleneck here, but with NFV nice, as and how you increase the chain length, you are still able to get and try to meet the right throughput. Okay, so overall, like the numbers that we are trying to say is you are having less impact on the normal operation, and you are having good work on the performance that you see otherwise with FTMB and Pico without much of the overhead. Okay, so yeah, this sums up the reinforced work and how we are trying to achieve overall. So I tried to see like whether we can go over the another interesting set of work, but since we don't have much of a time, I've just tried to give you a brief summary of what we are trying to do in this work. So now you know that many works have come in terms of trying to use the edge, because if you have to go to cloud, you suffer higher latency. And at the edge, you can deploy a lot of resources, but a lot of functionalities, especially the AR, VR, that require you to do inference, right? So we try to work around in the same space and see what is the thing that we are seeing here. And recently we got the publications here at SEM SOCC and in CloudNet a week ago, which also got us the best paper award, student paper award. And here our approach is trying to see how you can utilize the GPUs at the edge clouds and efficiently do the bundling and sharing of the resources. I'll not get into any of these details yet, but I think the interested folks can go over and see how the things are. But to quickly summarize my work or our work that we are looking for and the way we are proceeding, I try to address this NFV cloud performance, orchestration, and resiliency aspects. And the future research that we are looking forward to is the serverless computing, which I'm not sure if you'd have heard. This is the main phenomenal shift that's happening, and most of the companies are going towards this. And there are several opportunities in terms of looking at job scheduling, service reliability. How do you manage security now for these serverless jobs? All of these are currently in research that we are looking for. And also on the smart NICs, if you want to use regular programmable NICs and leverage them for multi-tenant high performance ML and inference platform that our earlier work built on, and see that overall these things, how we can club together in terms of the application perspective, trying to use the edge, 5G, and where the low latency and deterministic delay is a crucial requirement. And especially with the growth of IoTs, we see there is a lot of space, the way we can try to manage, and our research is currently focused on these directions. Okay, so with this, I would like to conclude my talk. And again, thank you for this opportunity.